Hello. Today I would like to talk a little bit about an insight I had at some point into the electric field strength equation. And I kind of just wanted to share that. I find it pretty interesting. And so here's the screen. Up here's a little review. Of course, this is how we calculate the electric field vector using Coulomb's constant, K sub E, the charge of whatever the particle has, and then divided by the shortest distance from that charge that the point that you're interested in is squared. And it's always pointed either radially outwards for positive charges, so this would be a positive Q, or radially inwards for a negative charge. And I had said before that this is another way to calculate it because Coulomb's constant is defined as 1 over 4 pi times epsilon sub naught, which is E sub naught's the permittivity of free space. So this would be in a vacuum. And so we can write the equation in this way. And I had kind of hinted at this 4 pi r squared in the denominator of this right equation to calculate the electric field vector, and asked if you had recognized that equation. And so we're kind of going to discuss where that might come from as far as the model goes. And of course, the model is just our way of describing the phenomena of electricity and electric fields. So firstly, I'm going to go ahead and start out by saying that field lines can only emanate or terminate at a positive or negative charge respectively. So field lines, electric field lines only emanate from positive charges, and they only terminate at negative charges. So in other words, if I have these field lines drawn over here on the left, one can't just randomly appear in space. It has to start at a positive charge and it must end at a negative charge. So for this reason, I'm going to go ahead and define that based on the charge, there will be a greater number of field lines in the model. So in other words, if I have 6 electric field lines drawn for this plus Q, if I had plus 2Q, I would double the amount of field lines for this model. So we now see that the number of field lines in the model is based on the quantity of charge that you have. So let's go ahead and let the charge divided by that proportionality constant E sub naught, let's define that as the number of field lines emanating or terminating from a charge. And this drawing over here, they're emanating from a charge because it's positive. Okay. So we know by the equation that, for example, you see this dashed circle I have around Q, the electric field strength is going to be the same at all points of equal radius around this charge. Of course, the direction of the field is going to be radially outwards, so that will be different. And we know that the electric field strength in this on this radius, the smaller radius R1, is going to be greater than the electric field strength around this larger radius R2. And here's a thought I've had as to why that might be. So I'm going to try to couple the electric field strength with the electric field line density. So in other words, not just how many electric field lines there are, but how many electric field lines there are per square meter of surface area. So in this case, we have a sphere's surface area because a sphere in 3 dimensions would be equidistant from the charge at all points. And so the field strength should be the same. And so if we go ahead and say, okay, I'm interested in the electric field lines area density, then what that would tell me is that the electric field strength is equal to the number of field lines, which we've just defined as linearly proportional to Q times or divided by some proportionality constant. So this is the number of field lines, and then we'll divide by the surface area of a sphere. Of course, a sphere has all points equidistant of a single radius. So we'll go ahead and divide by the equation for the surface area of a sphere, which happens to be 4 pi r squared. And so what this is the number of field lines, electric field lines, per surface area. And of course, when we rearrange a little bit, out pops the equation for the intensity of the electric field, or the electric field strength, which is Q divided by 4 pi r squared times the permittivity of free space. That's the second equation up here, which is why I think it's more beautiful and insightful, because the 4 pi r squared kind of pops out after a while. Whereas with this equation on the left, you may be left wondering, why is it that this inverse square law exists? Why, if you double the distance away from the charge, do you divide by 4 the field strength? Or in other words, if you half the distance from the charge, you quadruple the field strength. So this is kind of how I think about why that might be. And then another fun thought, okay, so we live in a 3-dimensional world. What if we lived in a 2-dimensional world? What might the electric field equation look like for electric field strength? Well, in this case, in the 3-dimensional world, we use surface area of this manifold that's a sphere. But in 2 dimensions, there would just be a circumference, right? The field lines would emanate through a circumference because they couldn't come out of the page. This would be in 2 dimensions. So I wonder, I have no idea whether this is true or not, but I wonder if you could use the same logic and say that the electric field equation for the electric field strength in a 2-dimensional world would be the number of field lines, which will leave that as Q over the permittivity of free space, divided by the circumference, right? So now we have like a density of field lines through the circumference. That would be 2 pi r. And so we might end up with an electric field strength equation of Q divided by 2 pi r E0. In this case, the inverse square law possibly wouldn't exist. It might just be the field strength would decrease proportionally. So if you double the distance, you half the field strength, or half the distance, double the field strength. All right, so I think that's all I have to say for this video. The second part is pure conjecture. The first part is too. It's just kind of an interesting way to look at the model. So definitely not anything that's necessarily going to help you on homework or tests, but just something that I found interesting. Well, I hope you enjoyed this video, and I'll see you next time.